Jai Hind students, welcome to my YouTube channel. Students, before the start of the session, every time I just have a tendency to share the life lessons with you. Actually, the life lessons, they are defined as an experience that teaches you how to behave better in a similar situation in the future. Lessons can also be learned by watching others or receiving teachings from others about the life lessons. So lessons definitely help us grow as an individual in understanding that all our actions have consequences. So you need to heed the lessons that life teaches you so that you may become a better version of yourself. Students, I always use these experiences or these lessons so as to motivate you, so as to inspire you to take action so that you may live your dreams. So please, whatever experiences I tend to share, try to grasp it, try to learn about it and try to implement in your life so as to make yourself a better person, a better human being, so as to realize your dreams. So students, with that, let's start with this particular session. We are going to start a new unit, which is electromagnetic induction. It's a wonderful phenomenon, and actually I'll start with a brief history. I'll introduce this topic with the fact that in 1820, Christian Hans Oyster, he was a Danish scientist, he experimentally verified the magnetic effect of current, which we have already studied and we are aware of. Magnetic effect of current is whenever a current is made to pass through a wire, then magnetic field gets established around its vicinity, around its surroundings. So the production of magnetic field around the vicinity of a current carrying conductor is magnetic effect of current. Actually, when we place a magnetic compass needle near a current carrying conductor, it shows some deflection, isn't it? So definitely it proves the existence of magnetic field around the vicinity or the surrounding of a current carrying conductor. So this is magnetic effect of current, which was discovered by Oyster way back in 1820. 11 years later, Faraday thought that if magnetic field is produced by current, why not the vice versa can happen? That is, why not current be produced from magnetic field? So, in 1831, 11 years after the discovery of magnetic effect of current, Michael Faraday discovered the electromagnetic induction phenomena, which is basically the phenomena of production of current in a coil when the magnetic field, or more precisely you can use the term magnetic flux linked with the coil, changes. So it's electromagnetic induction is the phenomena of production of induced EMF or induced current in a coil when the magnetic flux or the magnetic field linked with the coil changes with time, right? So before we start, we need to understand this term magnetic flux. Students, flux is a term associated with a surface. So in order to introduce this term, consider a surface to be placed in a region of uniform magnetic field. So flux through the surface is measured as the total number of magnetic field lines crossing through the surface normally. Suppose this is the surface and this is the magnetic field. So total number of magnetic field lines which are crossing through this surface held in the magnetic field normally means perpendicularly. That gives the measure of the magnetic flux. So again I repeat, flux, this is a term associated with a surface. Magnetic flux associated with a surface held in a magnetic field is measured as the total number of magnetic field lines crossing through that surface perpendicularly or normally. So students, basically you are aware, larger the strength of the magnetic field in the region, more will be the magnetic field lines in that region. and accordingly the magnetic flux will also increase. So changing magnetic field means changing magnetic flux. Decrease in the magnetic field means decrease in the magnetic flux. Increase in the magnetic field means increase in the magnetic flux. So Faraday observed that whenever there is a change in the magnetic flux linked with the coil, an induced current is produced in it. So the phenomena of production of an induced current or EMF. EMF stands for electromotive force. So the phenomena of production of an induced current or EMF in a coil whenever the magnetic flux linked with the coil or associated with the coil changes is known as electromagnetic induction. I'll represent it by EMI, electromagnetic induction. Clear, students? So the phenomena of production of an induced current or an induced EMF in a coil whenever there's a change in the magnetic flux linked with the coil. This phenomena is known as electromagnetic induction. And as I have described this term, change in magnetic flux is the change in the magnetic field. There are some other factors involved as well. But remember, flux is the measure of the total number of magnetic field lines crossing through a surface perpendicularly held in a magnetic field. So, greater the number of magnetic field lines crossing through the surface normally, the more is the magnetic flux associated with the coil. Right? So, students, before we start with the experiments which were performed by Faraday, let us watch a beautifully compiled animation which will certainly make you try to appreciate the efforts put in by Faraday and the conclusions which were done after the experimental observations, and those conclusions through the experiments were later known as the laws of electromagnetic induction. So let's watch this animation first.
It is inevitable that we all experience failure in the pursuit of success. In fact, Faraday probably failed more times than achieving success. But he kept trying. He didn't give up. Through the lows, he found the highs. Most great people have achieved their greatest success just one step beyond their greatest failure. When you take risks, you learn that there will be times when you succeed and there will be times when you fail. And both are equally important. Our failure don't define us. It's how we rise after we fall that actually defines us. Michael Faraday engaged himself in doing various experiments. He thought that if a current-carrying conductor can produce magnetic field around its vicinity, as was verified by Hans Oersted, he thought that the vice versa process, that is, the magnetic field can be used to produce current as well. So Hans Christian Oersted was a Danish physicist and chemist who discovered that the electric currents create magnetic fields, which was the first connection between the electricity and magnetism. Hans Christian Oersted found that when current is made to pass through a conductor, then the magnetic needle shows some deflection, which suggests the existence of magnetic field around the vicinity of current-carrying conductor. So, this proves that electric current produces a magnetic field. Michael Faraday thought that if current can produce magnetic field, then magnetic field must also produce electric current or induced current. So English physicist and chemist Michael Faraday was one of the greatest scientists of the 19th century. His many experiments contributed greatly to the understanding of electromagnetism. His main discoveries include the principles underlying electromagnetic induction, diamagnetism, and electrolysis. Faraday found that when the magnet is kept stationary with respect to the coil, then the galvanometer showed no deflection. But when he moved the magnet inside the coil, then the galvanometer showed some deflection, indicating the production of current. Therefore, motion of the magnet causes the production of current. Now what he did was, keeping the magnet fixed, he moved the coil towards the magnet. Now again the galvanometer showed some deflection. So he concluded that it is the relative motion between the magnet and the coil that is causing the current to get induced in the coil. Now Faraday, keeping the coil fixed, moved the magnet out of the coil. So again he found deflection in the galvanometer, but in the opposite direction. So again indicating that the current is now being induced in the coil in the opposite direction. So he tried to reverse the poles of the magnet. Faraday repeated the experiment and he once made the magnet to enter the coil and then he took the magnet out of the coil. He found the galvanometer to show deflection in both the directions. So the following points were concluded. If north pole goes inside the coil, then the deflection of the galvanometer was towards right. If the north pole comes out of the coil, then the deflection is towards left. When south pole goes inside the coil, then deflection was towards left. And finally, when south pole comes out of the coil, then the deflection was observed to be towards right. Now Faraday tried to move the magnet faster with relative to the fixed coil. So he observed that faster the motion, more is the deflection in the needle of the galvanometer. That is, more the rate at which the induced current is produced. So, on the basis of his experiments, he concluded the following points. So, current is induced due to the relative motion between the magnet and the coil. Deflection reverses when the poles of the magnet are reversed. This direction of the deflection shows the direction of the flow of the current. And faster motion of the magnet or the coil causes a faster deflection, that is, the rate at which the current is induced in the coil. So, these observations were collectively known as Faraday's laws of electromagnetic induction. This production of electric current across a conductor when exposed to a changing magnetic field is known as electromagnetic induction.
Let us discuss some experiments which were performed by Faraday which led to the laws of electromagnetic induction, right? So first and foremost, we will discuss how induced current is produced in a coil whenever there is a relative motion between the coil and the source of the magnetic field. So let's discuss experiment number 1, that is when the source of the magnetic field is moved towards or away from a stationary coil, right? So this is a coil in which a galvanometer is connected, no source is there. It can be considered to be the S coil. Actually it is the secondary coil. There is another coil where a source is connected, so it acts as a source of steady current, isn't it? And this can be considered to be the P coil, which is actually the primary coil. Now students, we are aware, whenever current is made to pass through a coil, then it acts as a magnet. Its two ends, one end will behave as the south pole, the other end will behave as the north pole. So it will act as a source of magnetic field. P coil will act as a source of magnetic field, right? So as a source of magnetic field, either you can consider a current carrying coil or you can consider a magnet. Both are same thing. So this is OR. So this is the P coil. Actually this is the S coil. And this is the substitute of P coil, which will act as source of magnetic field. Right, students? So again I repeat, these are the two coils. One is the S coil where a galvanometer is connected, no source is there, and the other one is the P coil where a source is connected so as to make a steady current flow through the coil. Right? So this will act as a source of magnetic field. In place of this current carrying P coil, you can also use a bar magnet. Now students, what Faraday observed was keeping S coil stationary. Keeping this S coil stationary, if the P coil is brought closer to it, then he observed that the galvanometer gives some deflection, say towards right. It shows them some deflection, say towards right. So, galvanometer is a sensitive device. The deflection of it shows the production of current, the flowing of current through the S coil. So it means that when this P coil is brought closer to the S coil, then some current gets induced in the S coil. That is the reason why the galvanometer showed some deflection, say towards right. This was the first observation, right? Second, what he observed was when he moved the P coil away from the S coil, like this. When he moved the P coil away from the S coil, then also he found the galvanometer in the S coil to give some deflection, but this time in the opposite direction, say towards left. This is the original position of the pointer, right? This is the original position of the pointer. So in case P coil is moved towards the S coil, then suppose the galvanometer gives deflection towards right, and in case the P coil is moved away from the S coil, then the same galvanometer is found to again give deflection but in the opposite direction, so that is towards left. So what he concluded was, during the relative motion between the P coil and the S coil, now relative motion, keeping S coil fixed, P coil can be moved towards or away, or keeping P coil fixed, S coil can be moved towards or away, right? So relative motion, whenever there exists a relative motion between these two coils, or rather between the coil and the source of the magnetic field, then a current gets induced in the coil. And in both the cases, the current so induced is in opposite direction. That is, in case of bringing P coil closer to the S coil, if the galvanometer shows deflection towards right, then on taking the P coil away from the S coil, the galvanometer gives deflection towards left, indicating now the current produces in the opposite direction as was in the earlier case. Clear, students? And as I stated earlier, in place of P coil, you can simply make use of a bar magnet. Both, either a current carrying coil or a bar magnet, both will act as a source of magnetic field. Now, there is another very important observation. In the absence of any relative motion, that is, when both are kept stationary, none of the coil or the source of magnetic field is moved, right? Then the galvanometer is found to show zero deflection. The pointer remains in its original position, indicating no current is produced in the S coil. So, Faraday concluded that the current is produced in the S coil only when there is a relative motion between the coil and the source of the magnetic field. Now, relative motion means this can be kept stationary, this can be moved towards it, or this can be moved stationary and this can be moved away, or it can be kept stationary, it can be moved towards it, or it can be kept stationary and this coil can be moved away from it, or both can be approached towards each other, or both can recede away from each other. So these are the various cases in which the relative motion can exist. But in case both the coils are fixed, are held stationary, then due to the absence of any relative motion, the induced current in the coil is found to be zero. No current is produced in the coil. Right, students? Another very important observation made by Faraday was that suppose if I bring the coil P to the stationary S coil slowly like this. So obviously, as I stated, it will show some deflection, say towards right. Now what he did was he made the motion faster. That is, P coil is now brought closer to S coil faster, right? Like this. So in that case, the galvanometer, which earlier was giving deflection, slight deflection, now it shows, this is the original pointer position, now it shows large deflection. Now it shows large deflection. Large deflection, the galvanometer means the production of induced current whose magnitude is large. Similarly, by keeping the S coil stationary, when this coil is moved away at a faster rate, then again the galvanometer shows deflection in the opposite direction, but the deflection is found to be large. Again indicating that the induced currents produced in the coil is of large magnitude. So, what he concluded was, faster the motion, faster the relative motion between the coil and the source of the magnetic field, the more is the current that get induced in the S coil. Right, students? So again, I will repeat the conclusions from these experiments. First conclusion was, whenever there is a relative motion between the coil and the source of the magnetic field, then the galvanometer shows some deflection indicating the production of current. Right? It happens because as we move the coil P closer or away from the S coil, then the magnetic field associated with S coil either increases or decreases. That is, it changes. So whenever there is a relative motion between these two, there will be a change in the magnetic field linked with this coil. And whenever there is a change in the magnetic field linked with the coil, induced current is produced. Right? In case both are held stationary, then in the absence of relative motion, there will be no change in the magnetic field lines crossing through S coil. So in the absence of any change in the magnetic field, current induced in the coil would be zero. And students, most importantly, the faster the relative motion between these two, the more is the magnitude of the induced current so produced. So basically, the magnitude of the induced current, it is not only dependent on change in the flux or change in the magnetic field, it depends upon the rate at which the magnetic field or the magnetic flux linked to the coil changes. So that's a very important conclusion. I repeat, induced current or the induced voltage which gets developed in the coil, that depends upon the time rate change in the magnetic field or the magnetic flux linked with the coil. Right? How fast the magnetic field lines is changing. So that depends upon the time rate change. Clear, students? So this were the conclusions which led to the laws of electromagnetic induction. Right? We will discuss some other experiments as well. Let us consider, students, in the second experiment, these two coils, P coil and the S coil, be wound on a common iron core. This P coil consists of a source as well as a tapping key. Now this is a tapping key, means when it is pressed, then the circuit becomes closed and the current flows through the circuit, right? And when it is released, then the circuit becomes open. In such a case, the current flowing through the P coil becomes zero. And there is another coil wound on the same iron core known as the secondary coil. And a galvanometer is connected over here, right? Galvanometer is a sensitive device, the deflection of which will indicate the production of current, right? In the case of no current flowing through the S coil, the pointer of the galvanometer will show zero deflection. Clear? And here, I must make it very clear that on pressing the tapping key, the current which flows through the P coil is known as transient current. It is actually known as transient current. Students, it is that type of current which takes some finite time to grow from zero to maximum value. and then again on releasing the key, it will again take some finite time to decay from maximum to zero value, right? So it is not that when the switch is made closed, the current will abruptly attain its maximum value. It will instead take some finite time to grow from zero to maximum value. Similarly, when the tapping key is released, the current in the circuit won't abruptly become zero. It will take some finite time to decay from maximum to zero value. So such type of currents which take some finite time to grow or to decay is known as transient current. So I have depicted the current versus time graph over here, right? So as the tapping key is pressed, what happens is current grows from 0 to maximum value, right? So T1 is the time period during which the current in the P coil grows. If the tapping key is kept pressed, then more or less after time T1, the current in the P coil will become steady. This is the steady current. This is the steady current, means constant current. And then again switch, when the tapping key is released, then current won't get abruptly zero. Instead, it will take some finite time to decay from maximum to almost zero value. So T3 is the time during which the current has decayed from maximum to zero value. So students, it's pretty clear. During this interval T1 and during this time T3, the current is changing. Here the current is increasing, here the current is decaying or decreasing. And during the period T2, the current in the P coil remains steady. It's pretty clear, right? So now what Faraday observed was, when the tapping key is pressed, then the galvanometer in the S coil shows some deflection, say towards right. When the tapping key is kept pressed, if it is kept pressed, then he found that the galvanometer in the S coil shows no deflection. And again, when he releases the key, when he releases the tapping key, then he found the galvanometer to again show some deflection, but this time in the opposite direction. So these were the observations made by Faraday. Let me explain the conclusions and the reasons behind these observations. Now students, when the tapping key is pressed, so we'll encounter this time. This is, as I stated, this is the time during which the current in the P coil grows. So as current grows, the magnetic field linked with this coil will also grow. Magnetic field lines will grow. Magnetic field will change. It will increase. Due to the change or due to the increase in the magnetic field linked with the S coil, an induced current is produced. So the galvanometer will show some deflection. Right? Second observation was, when the tapping key is kept pressed, then the galvanometer shows zero deflection. What it suggests is, as the tapping key is kept pressed, we will enter this time period, that is T2, during which the current is constant. Here, current is steady or constant. If current is constant, you are aware magnetic field is directly proportional to current. So if current becomes constant, the magnetic field will also become constant. So the magnetic field linked with S coil during this time T2 will not change. So therefore, no current is induced in the S coil. So the galvanometer shows zero deflection. Third observation, when the tapping key is released, then we'll enter this phase. That is, for time T3, the current will decay, current will decrease. As the current decreases, the magnetic field linked with P coil and hence with S coil also starts decreasing. So magnetic field with the S coil is changing. So again, induced current is produced. But now this time, the induced current is produced in the S coil due to the decrease in the magnetic field. So now the current so produced is in the opposite direction, as was produced in the S coil due to the increase in the magnetic field in the first case during the growth of current. Right, students? So again, what Faraday concluded was, galvanometer shows deflection in the S coil, or induced current is produced in the S coil only when the magnetic field linked with the S coil changes. When I say magnetic field changes, it means that magnetic field can either increase or magnetic field can decrease. Right? Once the magnetic field stops changing, the induced current in the S coil will become 0, as is evident when the caliper shows 0 deflection when the tapping key is kept pressed, right? So these were the conclusions made by Faraday after performing this particular experiment, right? Okay, in this experiment, which is the third one, the coil is moved in a stationary magnetic field, right? So what we consider is PQRS. It's a region of uniform magnetic field. Uniform means constant. Constant magnetic field means in a region, if the magnetic field is uniform, it means that the strength of the magnetic field as well as direction remain unchanged, is constant, right? So let us assume PQRS to be a region of uniform magnetic field. And students, this cross, this symbol indicates the magnetic field is perpendicular to the plane and directed inwards like this. Magnetic field is directed inwards like this. So in the region PQRS, the magnetic field is directed perpendicular to the plane of the board and directed inwards. Here I have written cross means that magnetic field is directed inwards and perpendicular to the plane, right? And this is any coil. ABCD is any coil, right? Connected with a galvanometer as shown on the figure. Now students, what Faraday observed was, if this coil ABCD is moved inside the region of PQRS, inside the region of this uniform magnetic field, then he found that the galvanometer showed no deflection, that is, no induced current is produced in the coil, right? Now, second observation is, when the coil is moved outwards, like this, then Faraday found that galvanometer showed some deflection, say towards right. Third observation, when this coil is pulled inwards like this, then again the galvanometer showed some deflection. But in this case, the deflection in the galvanometer is opposite to that in the earlier case. So these were the three observations made by Faraday. Now let us discuss the explanation for these observations, right? Now students, first observation was, when this coil ABCD is moved inside the region PQRS. So moving the coil, which is well inside the region PQRS, the magnetic field linked with this loop will remain constant, because in the region PQRS magnetic field is uniform. So there is no change in the magnetic field linked with this coil ABCD. And in the absence of any change in the magnetic field, no current get induced. So therefore galvanometer will show zero deflection, right? In the second scenario, when the coil ABCD is made to, or it is pulled outwards like this with a constant velocity v, say like this. So as it is moved outwards, the effective area of the coil, which is under the influence of magnetic field, it will keep on decreasing. Like the coil will keep on moving in the outward direction. So I am talking about this effective area. At this instant, the effective area is this one, right? As it will go further outward, the effective area of the coil, which is under the influence of the magnetic field, will keep on decreasing. Therefore, the magnetic field linked with the coil ABCD will also start decreasing. Magnetic flux will also start decreasing. And as a result of change in the magnetic field or change in the magnetic flux linked with the coil ABCD, an induced current is produced. And hence the galvanometer shows some deflection. Now students, when the coil is moved inwards like this, so what happens is the effective area of the coil, which will be under the influence of this uniform magnetic field, will keep on increasing. So now again induced current will be produced in the coil, but it is due to the increase in the magnetic flux or increase in the magnetic field linked with the coil ABCD. So here again induced current is produced, but in the opposite direction. So this experiment further validates the fact that induced current in the coil will exist or it will last as long as the magnetic field or the magnetic flux linked with the coil keeps changing with time. Once the magnetic field linked with the coil or the magnetic flux linked with the coil stops changing, it becomes constant, then induced current will also become zero. Clear students? And another observation which Faraday made was, if it is pulled outward or inward at a faster rate, then the galvanometer shows deflection, but it shows appreciable deflection, indicating that the magnitude of the induced current so produced in the coil also increases. So here lies a very important conclusion, that the magnitude of the induced current so produced in the coil, it not only depends on change in the magnetic flux or change in the magnetic field, it depends upon time rate change in the magnetic flux linked with the coil. So faster the motion, faster the change in the magnetic field or the magnetic flux linked with the coil appears, the more will be the magnitude of the induced current so produced in the coil. Right? So these were the observations, explanations and the conclusions of these experiments. So students, in this episode we have discussed about magnetic flux, its theoretical concept, then the phenomenon of electromagnetic induction, then we have watched an animation regarding the experiments performed by Faraday and the conclusions, observations, and we have discussed some other experiments as well, signifying the production of induced current by various methods. So ultimate conclusion is induced current is produced in a coil whenever there is a change in the magnetic flux or magnetic field linked with the coil. So whenever there is a change in the magnetic flux or change in the magnetic field linked with the coil, an induced current gets produced. So this phenomena is known as electromagnetic induction. And the magnitude of the current so produced, it does depend upon the rate at which the magnetic flux changes. So the strength of the induced EMF or the induced current produced in the coil is dependent upon the time rate change in the magnetic flux associated with the coil. And students, induced current will last in the coil, will exist in the coil till the magnetic flux linked with the coil keeps changing with time. Right? So that's it for this particular session, students. We'll continue in the next lecture then. Do join me.